Hello everyone, welcome back to Beauty and Simulations. I am Lakshman Anumolu. In the previous video, we have prepared and rendered a basic studio which we will be using to prepare scenes for our CFD simulation results and render them. In this video, we will prepare a scene file for results from Dambreak problem. We will render the scene with two different settings that will produce these animations. As this is the first CFD result for which we are going to produce photorealistically rendered images, we will be discussing some general guidelines and details while preparing a scene. This video will be longer than the rest of the future tutorials, where we will be simply touching the scene file and get to the rendered images in substantially less amount of time. For those of you who are new to multi-phase flow simulations, Dambreak test is one of the benchmark cases that is used as a verification or validation test for two-phase numerical solver. There are many variants of this test. For this video, I have prepared a canonical case with custom dimensions and simulated using two CFD softwares. One is OpenFOAM, the other is Converge. Both these softwares have two-phase flow solvers and can write the fluid interface in wavefront OBJ format at runtime. This case can be simulated using the Interfoam solver available in OpenFOAM. I have uploaded the test case setup, which you can download from the link in the description of the video and simulate using OpenFOAM. Note that this setup works with both OpenFOAM 7 made available by OpenFOAM Foundation, and it also works with OpenFOAM v1912 developed by OpenCFD. I have also made all output surface files in wavefront OBJ format available to you. If you do not have OpenFOAM installed, you can download output files from here and render scenes using the steps we will be discussing in this video. I will show the links again shortly. They are also made available in this video's description. Before you proceed to download these output files, I want to direct you to another set of files that are generated from Converge. I would recommend you to download them. Because of the way the fluid region is nearly closed. If you are a user of Converge, you can simulate this test case using these dimensions and the properties of fluids. I have made all the surface files generated from this case available in the link shown. Again, all the links are presented in the description of this video. Since we are aiming to prepare a photorealistic animation for Dambreak simulation in this video, you may continue with this tutorial by downloading the output. A note on the surface files from Converge and OpenFOAM. Consider a rendered image for the result from Dambreak simulation at a given time. The corresponding triangulated surfaces obtained from both Converge and OpenFOAM look like these. Converge writes the interface by nearly triangulating the entire fluid region, whereas the output files I uploaded for OpenFOAM do not close the fluid region. Though for some simulations it does not matter much, for some if the surface is not closed, the resulting image may not look appealing. For instance, in this very example, you can notice that we are looking directly at the bottom side of the studio, but not through the fluid. Due to these differences, while working with this tutorial, I would recommend you to download output obtained from Converge. I will be giving my demo using these in this video. But if you prefer to simulate using OpenFOAM, everything we are going to discuss in this video still holds, and you can also get pleasing results by simply tweaking camera positions and changing the view directions. Please download required files from these links. Also note that if you are simulating a case where the entire liquid lies within the domain without touching the boundaries, then the results from OpenFOAM also look appealing. For example, liquid jet in crossflow or liquid injected into a pressurized environment. Before we start preparing the scene file for Dambreak results, I will present a few steps that I generally use in my workflow. I would recommend these while you start rendering your results in the beginning. Once the simulation is complete, copy or move the surface files into the mitsuba-renderer directory of scene templates and keep them in a folder named surfaces. Let me make a minor Git related comment here. The scene templates Git repository will not track a folder with name surfaces. Hence, if you accidentally try to commit changes to Git in future, these will not be added. If you are not familiar with Git, you need not worry about this comment. Okay, let's move on. If you have rendered multiple results, you may have many scene files, and you may have included some basic settings in all of them. Once you have done this multiple times, you will feel comfortable reusing some scene files, so that you need not prepare a scene from scratch every time you render your results for different simulations. For example, while working with this tutorial, you may use studio.xml as a template. As you may notice, the template file that I will use while preparing a scene in this video and some of the rendered animations I made so far is generally a copy of studio.xml. While preparing a scene file and before using it to render all results, it is generally a good idea to test it on few of the test case results. For example, you may have 100 output files from the simulation. It is generally a good idea to test the scene file we prepared on a subset of them. You may consider one in the beginning and few in the middle and one from the last. Specific to Mitsuba, it may also be helpful to reduce the sample count so that you can render a scene quickly. Though the image will be of low quality, it will give us a general idea of how the rendered image looks like for a subset of overall results. In case you felt like I threw some buzzwords here, please don't worry. We will go through this workflow practically in this video. You will get a clear idea of what I am referring to. Finally, if someone has prepared a scene file for their results and made it available publicly, please do not hesitate to go through those. You may learn new things that you have not seen earlier. Also, if their rendered image looks appealing, you can reuse the material properties in your results. This will save a ton of your time as our goal is to render our CFD results photorealistically without spending too much time. Also, if we borrowed a particular section from others, it is a good idea to give credits to them by simply adding a comment in our scene file. Well, these are overall the general guidelines that I use in my workflow. Feel free to modify and follow in a way that increases your productivity. For example, you may want to render results while the case is still running, so it wouldn't be ideal to move the directory with surface files to another place, in which case you may want to just render right in the case directory, and some other similar things like that. Let's get started with preparing a scene file to render Dambreak simulation results. By now, you may have cloned our repository from GitHub. If you have not already done this, please do so using git clone command and place it in a location of your choice. I will begin by downloading surface files obtained from Converge. Feel free to download any of these or by running the simulation by yourself. We have multiple files here. I uploaded two different folders. This one that starts with Dambreak_interface contains 250 plus surface files, written at all output timestamps. The other one contains a sample of 4 surface files. I will download the one that has just 4 outputs so that I can get to work quickly. The other files you are seeing here are simply uploaded with different compression formats. You can download whichever one is compatible for your operating system and fastest for you to download. In case you are unsure of the compression format, just get the .zip ones. Alright, let's get this one. I moved the downloaded file to mitsuba-renderer folder where I will be working on Dambreak scene file. Let's extract this and I will rename this to surfaces. Note that as I told earlier, Git will not track this folder. I will delete this one. Let's take a quick peek into surfaces folder. Okay, let's copy these output files back into surfaces folder. Delete this one. Now we have all the output files in the surfaces folder, which we will be using to render our scene. I will use studio.xml as a template. So let's make a copy of it and rename this to dambreak.xml. This name sounds fair. We also need to make a copy of renderstudio.sh file. This is the script that calls this XML file to render the scene. I will rename this to render Dambreak. Let's open these two files. Since this is a copy from studio.xml, it already has studio and arrows that point along the coordinate axis. Let's also open run singularity file, which is the one that we'll be using to call singularity. Here we need to replace render studio with render Dambreak. The workflow that uses run singularity, which calls render scripts, which in turn calls the required scene files, is presented in the overview video. If using these files is kind of confusing, I would encourage you to go through that quick overview video. After we made this change, we don't need to touch run singularity script throughout this exercise. Let's save this and close. We mainly need to modify dambreak.xml to prepare the required scene. Before working on the scene, let's prepare the render script so that it calls the scene file on each of our surface files. Remember, we have 4 outputs from Dambreak simulation stored in the folder surfaces. We will let the output saved into this folder. Let's not modify this. We can use higher number of processors if we have them available. I'll change this to 14. This one creates the output directory. We have to render this Dambreak scene on 4 output files. So let's write a for loop. I know that we have 100, 200 and 286 timestamps that were written. So I have hard coded them here. We can take a quick look at surfaces folder. This one contains 4 files and we have 100, 200 and 286. All of them padded with zeros so that they have 5 characters in their file names. Let's get back to this. Let's make some modifications to read the output files. Here we are calling Mitsuba with number of processors and output directory. Let's rename this so that we can save each output image with names 00001.png like that. And here it's not studio.xml, it is dambreak.xml. Let's save this. Finally, this script calls output files from surfaces folder on all those 4 files and calls this scene to render. We will need to make one more modification to this. We will get back to this later after we make changes to Dambreak file. For now, we don't need to do that. Before we start modifying the scene file, we will see the end goal. Here is the look we are aiming to get. Few differences we can notice from our basic studio are the camera position and target location are different. A wooden texture is applied to the sides of the studio. We have a glass box here whose dimensions match with the computational domain of the Dambreak problem. Finally, we have water here. In other words, this is the interface that we have in surfaces folder. We will need to make it look like water. Let's do this one by one. We will first begin by applying wooden textures. Just like how we have a non-emitting walls section here, to apply as default property to the sides of the walls, we will prepare another section to apply bitmap type texture to these sides. There is an image wood.jpg that is made available in textures folder. We will be applying that to the sides of the studio. I will write the section here. After it is done, please pause the video and update your scene file. I will copy this section. Let's rename the ID to wooden walls. And the texture type is bitmap. We don't need these things. What we have to do is we have to apply the image wood.jpg, which is a file. Let's write that down. It is in textures folder. The name is wood.jpg. Now we have to replace all these IDs with wooden walls. Let's copy this. For the floor, for back wall, for front wall, right and left walls. Let's save this and render the scene and see how it looks like. Wait, it's actually taking a long time. I don't want to wait for 30 seconds. Let's see what we can do. As mentioned earlier, we can reduce the sample count. Let's reduce this to 16 so that we can render the scene quickly. Rerun the script. See, it reduced from 30 seconds to 8 seconds. Okay, it's rendering the first image. We only need this. Remember, I have coded 4 in the for loop in bash script, so it's trying to loop through all 4 of them, but we have not linked to the output files, so we don't need to loop through all 4 of them. Let's see how it looked like the first one. We have it in images folder. Here it is. All the sides except the top wall, we have applied the texture wood. We completed one of the steps. For the next one, let's add a glass box here. For the glass box, we have a model box.obj, which is in the models folder. We need to load this into our scene. Let's talk briefly about this model. This is our model. Along x, it is of size 0.5 units and the same along z direction. Along y, it is of size 0.25 units. At the bottom, it has some thickness of size 0.005 units. The bottommost layer goes into the negative y. So while making this part of the scene, we need to move this entire box along y-axis by 0.005 units. Let's render our scene with the box. Since we are going to load the box as obj file, we can borrow another existing section. I can recall that we used models to render arrows in our scene. Let's copy one of those. I'll copy axis X. I'll paste it above the studio section. Let's rename the ID to box and the model is box.obj. We also need to translate this along Y by 0.005 units. Let's copy the translate tag from the other part of the code from here. Let's paste it here. We have to translate this along Y by 0.005. We want to render this as glass. Mitsuba comes with a library of materials. We will model the box as dielectric material. Let's replace this. This requires both internal index of refraction and external index of refraction to be specified. Let's write that part of the code here. This specifies the internal index of refraction for the external index of refraction. Now we want to render the box as glass. Mitsuba provides some material names. Let's use acrylic glass for this one. And externally we want to use air. In case you know the numerical value of a material, you can replace this with that value. Instead of using the name here, you can use a numerical value. But if you use a numerical value, for example 1.49 or so, you have to replace this with float. Let's undo this. We are now ready to render. Before we render, let's make a small modification to our render script. This for loop is calling Mitsuba 4 times. This would be useful once we start rendering fluid. For now, let's only do it once. Let's render the scene now. Let's look at the result. Here it is. I think it is time to change camera positions. Let's do that. In the final look, all I was doing is I placed the camera along the middle section of this box and it is looking right at the center of the bottom surface of this glass. I moved the camera a little farther than the default value used in the studio scene, which means we can either move along positive Y or positive Z or both. Let's move slightly in both directions. Updating the camera positions is straightforward. Change the target to the center of the box but on the bottom surface. Our box dimensions are 0.5 along X and Z. So let's replace this with 0.25, 0.25. Let's move the camera along X to match with the middle section of the box, which is 0.25. A little along Y too. Let's make this 0.5. And for Z, I will use 0.8. Let's see how this looks. We now have a different look. We can see the entire box now. Let's add water to this. To load the fluid interface into the scene, I can copy the existing section prepared for the box. Let's copy this. Rename the ID to water. And for the surface file, I will hardcode to the first one, that is first file, and I know that these are in surfaces folder. For now, we will render the first scene like this. We will soon see how to pass the surface file through our render script. This time we are not going to translate along Y. In reality, this may have a slight effect, that is the surface goes slightly into the bottom layer of the box, which has a finite thickness, but it is going to look good. Finally, in this section, we will treat it as a dielectric. For internal IOR, this time I will use a numerical value, which is for water. Remember, we have to replace string with float, since I provided a number here. For air, I will use 1, though not exact, but a very close value. String to float here. We have the section ready. Let's save it and render the scene. Here we have the surface, which is kind of looking like water, and we have a box, we have the wooden floor. Let's add some more properties. So far, we have assigned surface properties for the glass box and the fluid region. But these two occupy volume, and to render the medium correctly, Mitsuba provides a tag called medium. We will treat these objects as homogeneous medium. Let's write few lines representing this. Make a copy of BSDF section here. Change BSDF to medium. Type is homogeneous. Apart from type, we also need to provide additional detail. The section we are going to prepare now provides information about the participating medium that lie on the interior side of this shape. So we need to specify that like this. If we are adding some info about exterior side, we need to use exterior here. But for this shape, we are only providing info about the interior side. This section requires couple of more details. We need to provide values for absorption coefficient and scattering coefficient for this medium. Let's write couple of more lines here. This one is for scattering and this for absorption. Feel free to play with these values to give a look for the medium that you like. Finally, we also need to change it here. I will copy this and use it for the glass box. I will use these values. Again, feel free to play with these and use whichever you like. Render one more time. This is the final rendered image with low sample count. Finally, we will see how we can pass surface files from the render script. Until now, we are rendering the scenes by hard coding the surface files. If we want to render few hundred images using a script, this approach is not feasible. In these scene files, we can use variables that can be passed through scripts by adding them as additional arguments while calling Mitsuba executable. For example, we can replace this path by a variable like this. Here, interface is the name of the variable. We can now pass an argument with this name while calling Mitsuba and assign a value to it right here. Let's add some code. Interface here will be referenced as $interface in the scene. What we are doing here is, for each for loop, for example, when I takes the value 1, count becomes 00001 and the interface takes the value surfaces 00001.obj, which is the surface file, and this is passed as an input argument to the scene file, and this is referenced with this variable inside the scene file, which Mitsuba will be using while rendering the scene. Before testing this alone, we will uncomment the rest of the input files and render all 4 at once. Let's save this and run the script. Here we are rendering 4 images using all 4 surface files. Here are the outputs. To reduce the noise that we are seeing in this image, we have to increase the sample count. You can render the scenes by increasing this value to 64 or more and render them again. If you re-render the images by changing the for loop from this to this, you can get the final animation. But note that you need to download another zip file that contains all surface files. Let's quickly make changes to the scene to get another look that we were seeing in the beginning of this video. Before that, let's undo this for loop, and for the scene file, we will this time use higher sample count. Let's use different values for the absorption coefficient for water. And we have to replace wooden walls with non-emitting walls. For the floor here, back wall, front, right and left. That's it. Let's run this. This one took slightly longer than earlier images due to the higher sample count we used. Before we look at the results, let me make a quick note about the sample count. The number we use for the sample count should be perfect squares. I mean, it should be either 4 square 16 or 8 square 64 like we used here, or 10 square 100. But if you use other values, Mitsuba will round it up to the next one. Let's take a look at the images. We have a different style ones now. Render all 200 plus output results with these new settings, then we can get this animation. In this video, we have seen rendering of our first CFD result using Dambreak case. We will practice more examples in upcoming videos. Feel free to use the settings that we have used for materials to give fluids the look we have given, or come up with different settings and share it with the community. You can submit your scene files by raising pull requests to the scene templates repository. I hope you all enjoyed preparing this scene and learned few things. Let's make this little addition to our amazing CFD community. Here are my contact details. Please feel free to ask any queries related to this video or drop a line with some feedback. Thank you for watching. Please subscribe. See you in the next video.